Hi everyone, I will present a joint work with Victor-Emmanuel Brunel and Arnak Dalalyan from CREST and Inthe Paris, which is entitled Statistical Guarantees for Generative Models Without Domination. Let me start with a simple game that you can play on whichfaceisreal.com. I give you those two images of faces, and one of them has been generated by a computer while the other one is real. You have to guess which one is which. So I'll let you have a quick guess. And the answer is that it's the picture on the right that is real, whereas the picture on the left, even if it's photorealistic, has been generated by a computer. So this impressive performance is possible thanks to new kind of generative models, which are called generative adversarial networks. It all started in 2014 with the seminal paper of Jan Goodfellow and his co-authors, which is entitled Generative Adversarial Networks. And since then, many versions and variations around the initial model have been proposed, as you can see on for example, on this website, the GAN Zoo, where you have hundreds of different GANs. So to make sure that we talk about the same thing, let me present a general GAN architecture and also the GAN problem. So let's say you have some real data, which are, for example, self-portraits of the painter Van Gogh. And you would like to be able to generate new portraits that could have been painted by him. So in order to do this, you'll design what we call a generator. Generator is a function, it's a mapping that takes as input a latent variable in a low-dimensional space and transforms it into an image. Okay, and the goal of the generator is to make this image look as much as possible as your real data. And in order to do this, the generator will show its images to a second guy, which we'll call the discriminator, and who has exactly the role you had when you had to distinguish between the real and the fake faces. Okay, so the discriminator will receive fake samples and real samples, and we'll have to tell which one is real and which one is fake. Okay, and based on this, the generator and the discriminator will receive training feedbacks and improves their ability to generate real images for the generator and to distinguish between real and fake for the discriminator. So at the moment, the theory of GAN is still needs to be done. It's mostly engineering how it's done GANs at the moment, and that's great because it leaves a lot of mathematical questions that need to be posed and answered. So we can first try to formalize the problem, then we can, inside this formalization, we can get theoretical guarantees for the algorithms that are used in practice, and so on. And so there are three pioneering work that has been done, all of them in 2020. So there are those two papers by Gerard Biot and co-authors, and this paper by Lucet, Pontil, and Siliberto, which I'll come back to later. Let me start with the problem formulation that we'll tackle. So let's say you have IID data in a high-dimensional space, which we call Y1, Yn. So think about images, for example. And actually, we don't observe those images. We observe noisy and contaminated versions, which we denote by X1 to Xn. Okay, and the goal here will be to design an algorithm that generates random samples from a distribution that's defined by our model, and which is as close as possible to the distribution of the data. Okay, so we'll impose a set of requirements on our model. The first one is that it should be easy to sample from our model. Okay, because we want to generate images, for example. Images live in a really high-dimensional and complex space, and even if I give you the density, for example, of faces in the image space, well, it's still really hard to generate samples. So we want to avoid this, and we'll be looking for procedure that give you easy to sample from model. Then the second requirement is that we want to be able to compare the distribution of our model from the two distribution with an error that can be interpreted as a sampling error, okay, because we're interested in a sampling problem. And if we just use those two requirements, well, the formulation is incomplete. We can just take the uniform distribution over the observed samples as a model, okay, which will you just resamples the samples that you already observed. But this is quite pointless from a generative modeling perspective because it doesn't yield any new sample, and you just see what you've already seen. And so we'll impose a natural third requirement is that the samples drawn from our model should be different from those that we observed. So we basically ask for our model to generalize with respect to the data that is observed. So those are some notations that I will be using during this talk, which are fairly standard. And since we want to get theoretical results, we need to make an assumption on how our data is generated, the data we observe. So we assume that there exists an ideal generator, G star, which goes from a low-dimensional hypercube to a high-dimensional hypercube, so just as in the GAN generator framework. And we have two sets of vectors. First set is what we can call the latent variables in the GAN models, which are IID uniformly distributed on the low-dimensional hypercube. Then the psi I to psi n can be seen as noise variables, for which we can control the noise magnitude with sigma. And finally, since we allow contamination in our model, we'll assume that a proportion at least 1 minus epsilon of our data follows this model. So what is this model? It means that the data we observe is just the image of the latent variable by the ideal generator plus some noise. And for the epsilon part of the data that's not inside of this, they can be distributed according to anything. It can even be adversarial. We don't make any assumption on this. This is a figure to just summarize what we assume. We have a low-dimensional hypercube on the left. We have a mapping G that maps those latent variables to a higher dimensional space. What we can see is that our data is close to a manifold for a large proportion of them, and at some points can be really far from the manifolds. Those are the outliers. Now we can define several quantities and formalize our goal. So we can define the oracle generator, which is the distribution of the data before adding noise and contamination. And for any candidate generator G, we can define the risk of this generator. So it's a measure of performance. And given a metric that we choose, it's just the distance between the distribution generated by this generator and the distribution of the data P star. And our goal will be to find a mapping, so it's an estimator that depends on the data, such that the risk is as small as possible. And in the simplest way to study this problem, first way to study this problem is to fix a smooth class of function, G, and we'll be looking to minimize the empirical risk over this class of smooth function. So we basically define what is an empirical risk minimizer for this problem. Okay, and the choice of metric that we make is quite important. We'll be looking at metrics that belong to a class of integral probability metrics, so they can be expressed as with this formulation. So it's basically comparing it's a distance between distribution, and it's comparing them using test functions over a class F. Okay, and classical examples are, for example, total variation or the Wasserstein-1 distance, if F is taken to be the set of Lipschitz functions. Okay, and under those assumptions and with the definitions I presented, we can actually control the risk in expectation of our estimator. So what we can show is that under the assumption, if the coordinates of the ideal generator are smooth enough, so if they belong to some alpha Sobolev space, okay, and if the class indexing the integral probability matrix is also smooth, then we can bound the expectation of the risk of our estimator as follows. So we have the infimum over all the class of the risk plus some terms that depends linearly on the noise level and on the contamination level. And then we have the dependence on the sample size. So what we can see is that we observe two regimes. First, we have the high smoothness regime, for which we have the parametric rate. And we have a low smoothness regime for which we get slow rates of type n to the power minus alpha over d. Okay, and the threshold is at the point d equal twice alpha. So that's the main result we can prove for our estimator. And we also show in the paper that we can get matching lower bounds. So let me talk a bit more about the prior works that I presented quickly earlier. So there was this first paper by Schreuder and co-authors, which established the large sample properties of the estimated distribution, but it assumed that the densities were dominated by a fixed known measure on a Borel subset of the high-dimensional space. And this is an assumption that we don't make because we do not assume any density anywhere, hence the title we gave to the paper. Okay, and then in the second really nice paper, Schreuder and his co-authors studied the case where the admissible discriminators are neural networks for a given architecture and obtain a parametric rate in this case. And finally, in the paper by Luis and co-authors, which is closer to what we do, they measure the quality of sampling through sinkhole divergence, so it's a regularized optimal transport metric, while in our case, we consider IPM, which maybe have a better sampling error interpretation, okay, even if we lose on the computational side. And they only consider classes of smoothness larger than the other two, while we consider all the smoothness. And in their case, they get the parametric rates just like us. So now I can conclude by saying that we introduced a general and non-parametric framework for learning generative models. And given the high-dimensional data, so for example, picture, we're able to learn the distribution in order to sample new data points that resembles the training one. And what's new in our case is that we allow the training samples to differ by some amount of noise and adversarial contamination. And we just assume that our data is close to a low-dimensional manifold. And what's important is that our bounds do not depend on the dimension, well, in the sample size, it does not depend on the dimension of the ambient space of the high-dimensional space, but on the low-dimensional space. And in this case, we derive the non-asymptotic bounds for the regret with rate of convergence that only depend on small d. And that's maybe the most important part of our work. So I thank you for your attention, and I will be really happy to discuss any question you might have.